Let's consider a closed system that has a boundary that moves. By now you should realize that we live beneath an ocean of air, and that's why the pressure is, almost 15 pounds per square inch of absolute pressure. That's quite a bit of pressure if you think about it. You probably remember seeing the rail cars implode from atmospheric pressure and other interesting phenomenon, but if you have a system that has a gas in it, that gas, as it expands, is going to do work. Now it has to do work against the atmosphere. That's one of the things that resists it. So even if there's nothing apparently attached to the piston, there's still work required to push the piston up. Now probably when you got into this course of study you understood a little bit about springs, and you may have been interested when you found that springs could be represented with a linear equation where the force varies linearly with distance. And you can actually calculate, if you've been through a physics class, you can probably calculate the amount of work that a spring does in moving from one position to another. And I've already given you an equation for that as well in this class. Have you ever thought about a gas that's expanding, like for example in your car's engine, when you put in the gasoline and the air and the gasoline burns in the air, now you've got high pressure, high temperature gas. What happens as that piston moves down? Well, the pressure drops. Why does the pressure drop? Well, there's more volume, right? So as the volume drops, as the volume increases, the pressure is going to drop. So how do you figure out how much work that gas does? I mean, if the pressure of the gas was constant as the piston moved and the volume increased, that'd be pretty easy, right? Because the force would be constant. Force would be equal to pressure times area, and it would be constant. But in the real world, it's not. And so how do you calculate these things? If you want to calculate the velocity that a projectile has leaving a barrel, how do you do that? The gases that are expanding and pushing the projectile, certainly their pressure is dropping as they expand. Now, it is true that we could consider the force that the gas applies over a small distance as work. Obviously that work's going to decrease. The force has to decrease because the pressure is decreasing. But for a really short distance, a differential distance, we could take the force to be constant. And in that case, the amount of work done by this moving boundary could simply be calculated as the boundary goes from state 1 to state 2 by just integrating the force over distance. So this is no different from what you've seen in physics. Work is just force integrated over distance. It's force times distance if the force is constant. We've already made it clear the force is not constant. But the force can be plugged in, and the differential distance can be plugged in here, and there's our equation. It just needs to be integrated, unfortunately. Okay, so what could we do with this? Well, the force is going to be pressure times area. Even as the piston moves, the pressure is going to drop, therefore the force will drop, but the force will be essentially pressure times area. Now, we're making some assumptions here. We're assuming that this is so-called reversible. And what that really means is that there's no fast expansion of the gas and there's no friction on the sidewalls of the piston, but we'll worry about all that later. It turns out, though, that this is a reversible moving boundary work. But we're going to replace the force being applied by pressure times area in our equation and see if we can make some sense of this. But if you stop and think about it, you might realize, well, wait a second, area is its own variable. If I multiply area times the differential change in the piston's position, that would be equal to the differential change in the volume of the system. So we could replace ADS with dV instead. And then our integral would look like this. So the boundary work would be the integral of the pressure as the volume of the system changes. So the pressure integrated over the volume between the two states. And that's how much work would ideally be put into the piston and then out of the system. Now all of that is nice to know, but frankly all you really need to know is this. Boundary work, when you have a moving boundary, is the integral of PdV. Now, to say that's all you really need to know is probably not fair, because I don't actually expect you to do much integration in this class. So I'll actually give you integrated forms of this equation. You just have to know when to apply them and when not to use them. So let's think a little bit more about this. We were talking about PV diagrams earlier, and a PV diagram is just a diagram where we can represent the state of the system at whatever point we wish, right? So if the piston, let's say, goes from state 1 on the left to state 2 on the right, we don't know exactly what that process path will look like. I mean, it could be all kinds of shapes, but let's just say it's some curve. Then the area beneath that curve would represent boundary work, because think about it, as the piston moves a differential distance on the horizontal axis or the volume axis, there's some roughly average pressure, and of course as that differential volume, or as that volume goes to a differential volume, goes to zero, then that's just one pressure. That product would be an area, but the area is a differential amount of boundary work. That's really what we're doing, is adding up area beneath this curve. So this equation, boundary work as the integral of PDV, just says give me the area under the curve on the PV diagram, and that's the amount of reversible boundary work that the system produces, or consumes, depending on which way the process path is directed. In this case, since the volume is increasing, then that would be a work coming out. It would be work produced. And you need to understand that this boundary work equation has a sign associated with it, an SIGN, a plus minus. And there's an assumption here. Basically, if the volume increases, right, and the pressure is obviously going to be positive, if the volume increases, well then that is positive work, and positive work is work coming out of the system. So if you have work going into the system, that would be negative work, negative boundary work. If you have boundary work coming out, then that is positive boundary work. Now, the process path determines how much work there is between the two states. It's not like a delta work, as we said before. The system could go through many different potential process paths, each one associated with its own amount of work. So the process paths we would choose would, if we're trying to produce work, would probably be one that produced the most work. But the area obviously beneath the process path is going to depend on the shape of the process path. Therefore, the amount of work produced is going to depend on that path. Now, if we considered a forward process and a reverse process where we net some work, where the work output from 2 to 1 is more than the work on path C from 1 to 2, well then maybe we could get some net work out of a system, and that would be pretty useful. And in particular, if we took path A, which would produce 10 kilojoules, and went back and reversed the process C from 2 to 1, well then that would only consume 5. So we would get a net work out of 5 kilojoules. Now you look at this and you might say, well, wait a second, is this some kind of perpetual motion machine? No, I haven't shown you all the details of each process. There would have to be, obviously, energy enter the process, perhaps in some other form, particularly heat, right? So that we can transform some of that energy into work. That's really what we're talking about here. There are special cases of boundary work where we can integrate that equation pretty easily, the integral of PDV. Sometimes, because of the nature of more the process, the way the container is shaped, or the way that the pressure depends on volume, sometimes gases' behavior in certain systems can be quantified as PV to the n equals a constant, where n is just a constant and c is just a constant that, if I expected you to use this so-called polytropic equation, you would have to be given those. I'd have to provide them to you, or provide them in some way where you could figure them out, right? If this is true, if the pressure times the volume of the system to the some power n, which I'd give you, is equal to a constant c, which I'd also have to give you, then that defines the shape of the process path. Understand that you could rearrange this thing, have pressure on one side, volume on the other, and you've got pressure as a function of volume immediately. And so that means that on a PV diagram, the shape of the process path is completely determined. Now, if that were true, then we could, as I suggested, rearrange the equation and write P equals C times V to the negative n. Remember, using rules of exponents on our exponent on the volume. And then, if we wanted to integrate that boundary work, well, we'd take the integral of P dV, but P can be written as CV to the negative n. And then, if you remember your rules of integration, the c just comes out. It's just a constant, so that's no big deal. V to the negative n, well, let's see. That's an x to the n dx type of term. So what do? Well, you just add 1 to the exponent, right? You evaluate at the limits adding 1 to the exponent. So it's v2 to the negative n plus 1 minus v1 to the negative n plus 1 divided by the exponent, right, which is negative n plus 1. This is just calculus. Now, if we rearrange things a little bit, we could distribute the constant through both terms in the numerator, flip the denominator around because I hate to lead with a negative sign. It doesn't matter. It's the same thing, 1 minus n instead of negative n plus 1. And then, if you remember rules of exponents, v to the negative n plus 1 is the same thing as v to the negative n times v to the first power, or just v. And so we can make that substitution as well, breaking up the negative n plus 1 exponent in both of those volumes in the two states. And then you might recognize that C times V2 to the negative n is just the pressure in state 2, just like C times V1 to the negative n is just the pressure in state 1 by our starting equation. And so we end up with an equation that allows us to calculate the amount of boundary work during a polytropic process. If for whatever reason we know that the process is behaving polystropically, then here is how we can calculate the boundary work. Now, because of the way the math works, there's a small problem. If the polytropic exponent n on the volume is equal to 1, then this won't work. Because look, in the denominator we would have 1 minus 1, that's 0, the whole thing blows up. So the calculus basically fails us at this one point. So if you understand all that derivation, that's great. But what you really need to know is what's in the box. Now, if we had a polytropic process that also involved an ideal gas, because understand polytropic processes don't necessarily involve ideal gases, even though PV to the n equals C looks kind of like an ideal gas equation. It's not. It's a totally different thing. But if we had a case where the gas behaved both as polytropic and ideal, then it would also be true that PV is equal to mRT, and we could substitute for PV in that polytropic equation with mRT instead, where P2V2 would just be mRT2, and we'd factor it out once we were done. So this is another good equation to have, but it's not as powerful as the first equation. It's not as general. This second equation here is only good for ideal gases that are also behaving polytropically. There are still other cases, though, and the question when you're told not to do something is always, well, what happens if I do it, right? So what if n were equal to 1? Obviously, we cannot use the equation we had a moment ago. This will not work because, as I said before, if n is equal to 1, then 1 minus n is 0. The boundary work blows up. It looks like we get infinite work, and that doesn't make any sense. Let's go through the calculus again. However, notice that this case, PV equals C, is the exact same case as an ideal gas that is at constant temperature. If we have some type of container, for whatever reason, it's an ideal gas and it maintains its temperature as constant, then what we're about to derive will be exactly the same. Because look, if the temperature is constant, and obviously it's a closed system, no mass is leaving, then mRT is also a constant. So we've got, again, PV equals some constant. I don't care what the constant is, right? It could be a polytropic equation with n equal to 1 and C equals some constant I give you. It could be an ideal gas at constant temperature, and the math would come out the same. Because, again, PV would be equal to C. In that case, all we have to do is rearrange and solve for the pressure in terms of volume. Well, that's easy. That's just the constant over the volume. So this is a 1 over x dx form. If you remember in calculus, 1 over x dx, well, how do you integrate that? Well, let's pull the constant out first, and it's a natural logarithm, right? So it's the natural logarithm of the variable evaluated between the two limits, the lower limit 1 and the upper limit state 2. So if we evaluate the volume at those limits, we write V2, right, natural logarithm of V2, minus, evaluating at the lower limit, natural logarithm of V1. And if you remember your rules of logarithms, when you have the natural log of something minus the natural log of something else, you can take the ratio of those two somethings as the argument in a single natural logarithm. Now, since the constant C is just P times V, we can plug in the pressure and volume in either state 1 or state 2. It wouldn't matter. This could be P2 V2 natural log V2 over V1, or as it is, P1 V1 natural log V2 over V1. Again, I don't care if you remember the derivation. All I care is that you remember this is the equation you use when you have a polytropic process with n equal to 1, or, now notice this is an or, not an and like the last time, or we've got an ideal gas at constant temperature. So remember, we had an equation that was a polytropic equation, and then we had that was a polytropic boundary work equation. Then we had one for a polytropic boundary work with ideal gas. So that was an and thing. You had to have both. This is an or thing, okay? You can either have a polytropic process with n equal to 1, or you can have an ideal gas at constant temperature, and this equation will apply. Now, I've given you 3 equations so far, technically 4 if you include the integral form, and if they are not in the summary at the end of chapter 4, you should add them, because any of these that are not there may be useful. So I highly recommend writing these in. You may have to back up the video and find them again, but they're worth writing down in the summary if they're not already there. The other thing you should note is what are the restrictions on the equation. When can you use that equation? Because one of my favorite things to do is give you a boundary work equation on your first exam and make you figure out which of the equations you need to use. So it's best to have them written down and know what the restrictions are on them so you can match it to the problem and then use it. So this is what you really need to know for polytropic processes with n equal to 1 or processes of ideal gases with constant temperature. Now there are other boundary work equations that I will show you, but we will investigate those later. There will be 2 more. You could probably derive the constant pressure integral, right? If the pressure is constant in the integral of PDV, that's a pretty easy integral to perform. I'll challenge you to try it. It's straightforward. You can probably get the answer easily. But there's also a boundary work equation for isentropic processes. I'll show you that one later once we know what an isentropic process is, but it comes out much like the polytropic equation. So we'll leave some space because we'll add those a little bit later.